gradient helps us to figure out minimum and maximum, and that will be the amazing application. Mountain or anything else, you drop the ball, where the ball gonna go? In this case, gradient will show us the minimums, but also we're gonna learn how to find maximums. These are amazing, cool ideas here. Because gradient is a collection of all directions at the same time with respect to x, y, and z. Gradient is derivative with respect to x, y, and z at the same time. So it shows you the fastest direction the function can get. And, let me just check this. Yeah, this is good enough. So the new chapter is called Minimum and Maximum. And we again going back to critical points, first derivative test and second derivative test. In which direction f increases the fastest? So this is going to the exam. I already saw the practice exam, and this question is there. So we're gonna ask you in which direction f increases the fastest, x squared plus y squared at 1, 2. And the answer will be the gradient direction. The gradient ascent or the gradient descent, later I will tell you this information terminology, shows you the fastest increase, fastest decrease. So I like this explanation in the Mario Kart, because you're all playing games. Which direction do you have to drive into to get to the finish line first? So that's exactly what is happening here. And previously we found what is the gradient for this function. Partial derivative with respect to x, that's 2x. Partial derivative with respect to y, that's 2y. Collection of those two gives you the gradient. So maybe you don't understand the question. That's why there's a nice graph here. The question is asking, this is a circle, x squared plus y squared equals 5. A circle. There's a point on a circle they chose. Here's the point, 1, 2 point. At this point, which direction should I go to increase my f the fastest? So maybe I should go this way, or maybe should I go this way? And it makes sense that the fastest way to get away from the curve is perpendicular way. That's what we learned before. And that is why gradient is used to find minimums or maximums, or where the function increases or decreases the fastest. There's a very nice explanation here. Intuitively, it makes sense. Intuitively, it makes sense. Because this is a level curve, x squared plus y squared equals 5. So f is constant when it's on the curve. Here, f is constant. To get away from being a constant as soon as possible, you need to go perpendicular to the constant. So to increase fastest, you need to point away from it. Analogy, it's interesting. If you are on the mountain or a cliff and your friend tells you to jump from it, you're not supposed to, but okay.
If you're a true friend, you will jump.
You usually jump perpendicular to the mountain, not tangential. That's the word, tangential to the mountain. So here's the cliff, and you're like, jump. Okay, let's be positive. There is like a lake there, okay? Then you just want to have fun. You jump. I do jump from the wave breakers in Ukraine. That's what I do as well. I like jumping. So I jump from the small cliffs, not a very big cliffs, but small cliffs. I do jump for fun. Even though there's a sign, don't jump. But again, Russians and Ukrainians, we know how to break the system. So we do jump a lot. Local snow where you can jump, not to break your legs. And then you jump towards the lake, not like here, where it's still a surface, right? So this direction will be a tangent, because tangent is close to your curve. This direction will be normal, because normal is perpendicular to the tangent. So it makes sense that this direction will take me away from the cliff very fast, while this direction I'm still on the cliff. Make sense? That is a pretty cool idea here. There was a question? No? So you can read this, and now write down this red fact. The biggest increase is the absolute value or magnitude of the vector of the gradient. So it is magnitude of all partial derivatives with respect to x, with respect to y, with respect to z, and so on. Find the gradient And that's one of the most fascinating applications of the gradient, is finding the biggest increase and the fastest increase and the fastest decrease. So here are the pictures more. And we were discussing today the AI, how AI is learning. AI is using gradient to find AI, artificial intelligence. You feed to the AI 1,000 hundreds of MRI images to detect tumor, for example. That's the recent study going on a couple of years on it. And then what is the fastest way to detect tumor? Here is the brain. And then there's some kind of dark piece over here. But computer only sees the whole thing. So should it spend lots of time over here? No. At some point, after thousands of mistakes, computer knows. Find a dark spot and go there, and then go around and be very careful. And the closest you get, just like you mentioned, the smallest, we were talking about this during office hours, the smaller the step size will be, because the closer you get, the more exciting it gets for the AI. Anyway, it's more precise. So this will be gradient. So it's pretty cool. Gradient has lots of cool applications, computer science, AI, and so on. I found you these cool animations to show you. This one you already saw. When you drop 3 different balls, where are they gonna go? What is the fastest decrease in this case? Depends on the location. Why? Because on each side, derivatives are different. So they will bring your objects or balls, whatever it is, to the different locations. This is a simulation also. All this is done by engineers and computer scientists, actually, not mathematicians usually, or applied mathematicians and numerical mathematicians, they do that. But mostly engineers, computer scientists code this. And think about it, such a simple question. So I'm dropping the ball on this curved surface. Where it's going to go? Such a simple question that we can play in the kindergarten with our kids. You had to go to Calculus 3 to finally learn mathematics behind it. No, this is serious how that the world is all based around mathematics, but it's getting so upper level, and that's why we cannot explain this to you. Even in high school, you have to get into partial derivatives to understand this with vector fields. Vector fields are coming next week. So how cool is that?
Kindergarten me, my mind is blown.
See? So I think I showed you this. Oh, this one is also cool. This shows the steps. What I just mentioned, the steps getting smaller the closer you get to the target. So first the computer does big steps, and then when it feels, there's a way to make computer feel that it gets them closer to the target, which is the minimum in this case, and we're going to learn this right now. The smaller the steps become, and you code it as a recursive function with the probability of the mistake and so on. Little arrows. Lots of chain rule is there. I mentioned in Calculus 1 class, AI is, you just missed the whole most important part. This was so interesting. Anyway, so same thing here, you see the steps. The idea of the gradient on every single step will be you have to go down from the mountain in complete darkness because you did not plan accordingly well. And then you only have a flashlight. You only see around you. That's all. So every step will be taking a derivative. You stepped here. Oh, it's going up. I don't like it. Step here. Yes, I feel it's going down. Now you're here. See the step? Okay, now my flashlight makes different circles. I see stepping here, going up, stepping here, dying because it's a cliff. Stepping here, smooth down. So I'm going here. Every single step, a human takes lots of derivatives intuitively to find a slope that takes you down. And that's how you climb, that's how you go down from the mountain at night. Does that make sense? So that's the best explanation people usually have for this class. So you don't have to write this down. Welcome to the highlight of the chapter on partial derivatives. The most important part is to figure out the maximum and the minimum of the function of several variables. It's exactly what we did with the first calculus with critical points. Again, missed the most beautiful part of my lecture. You guys should not be late. This takes me so much effort to prepare. Like, come on. We're going to do critical points, second derivative test, and all that kind of stuff, but with a twist. Let's do it. For now, the goal is to find local maximum and local minimum. Welcome back to the Calculus 1, but in 3D. Here it is. Write down the graph. So the graph, as you can see, is f has a local maximum at 5. 5 here has a coordinate 0, 0. That's local maximum. Remember what local maximum means? Local maximum means relative maximum. So it's not the biggest hill, but it is locally is a hill relatively to the neighborhood. In 2D, it was a little bit to the left and a little bit to the right. This is the biggest point. In 3D, it's literally a neighborhood. So around me, this is the top of the mountain, but maybe there are other mountains over there. And then as you can see, there are local minimums over here. Local minimums. Same thing, relative minimums. So they are locally little pits, or like, how would you call them? Yeah, pits. I like pits. How did we find those points? Who remembers? What's the magical word?
Math.
Mass, yes, it's a class for math, so it makes sense. Gradient, no, yes, but in calculus 1. Dun, 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 dun. Critical points. Critical point in 3D will be called a point or a stationary point. If, remember what we did, we found derivatives that equal 0 or d and e, but now we have many derivatives. So which one? All of them. And that will be a cool part of this. You have to find all partial derivatives and set all of them to 0 or d and e. And solve for critical point CPs. That's how I call it in my class, CPs. In the biology class, we call it CVs, critical values, and they're also critical numbers, blah, blah, blah. Same thing, different books. So, just like in calculus 1, local maximum or local minimum can be only at critical points, because remember we told you this word to be a candidate. Critical point is a candidate where you might have local maximum min. You don't have to check millions of points, just critical points. And that's why they call it critical, because something critical is happening there. At the critical point, a function could have a local maximum or minimum or neither. It's a candidate. So you only check them and then you say this one did not do anything, this one is max, 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 min. So just like before, find derivatives equals to 0, d and e. Why d and e? If you remember into d, who remembers why do we have to check d and e's? No. Derivative is d and e, not the original one. The cusp. The cusp might be a local minimum, but derivative there does not exist, right? Or local maximum. Cusps should be considered. Why not? It's like a pit with a very sharp corners. So we also have to consider that. And that basically most important part of the exam 2. Finding partial derivatives was a tool to do what? To teach engineers, biologists, computer scientists to find maximum and minimums. So let's do one example at least. Let's do that. Solution. Find critical points for the function. It's a polynomial force power, but now in 2 dimensions. Well, 3 dimensions. X to the 4 plus y to the 4 minus 4x minus 32y plus 14. What should we do? Solution. We just learned that we need to find critical. Step 1. Find CPs, right? So that means we need to find a gradient, and that's new for you. A gradient. And set it equal to 0. But 0, not a number anymore, it's a vector. So 0, 0. Like so. You don't have to write it down so complicatedly. Let's just do it step by step. Gradient is a collection of all partial derivatives. So we're going to find partial derivative with respect to x and partial derivative with respect to y. With respect to x is 4x cubed. Y to the 4 gives me 0. Minus 4x gives me minus 4. Everything else is 0. Make sense? F with respect to y. Who wants to tell me?
We have 4y cubed plus 32. Or minus 32?
Minus 32, amazing, thank you. My partial derivatives are ready. Remember in calculus 1, synonym of critical value, synonym of local minimum, increasing, decreasing was first derivative. This is what we did, but since we have many variables, you find all the first partial derivatives. Step 1, we did it. Step 2, right away, equals 0 and D and E. But it's polynomial, so we don't have D and E points here. Two polynomials, then they look fine for me. Solve each. Let me skip the solving in slow steps. Are you watching TikTok?
No.
X equals 1. X equals 1 here, and then Y equals, did anyone solve it? 2, thank you. I'll just skip. So you solve for each. Okay, those will be my critical points, but it's not very clear. So is it 2 points or it's 1 point? It's a critical point. Thus, it's one critical point with coordinates x comma y equals 1 and 2. So it's a location in 3D. That's what we just did. We're not gonna do test right now. I will show you in a second the second derivative test. But what do you think about that? Yes.
Is the xy the domain? Like, is that the projection of 3D, like on the xy plane? Instead of find, like,
No, you can find output. I know his question is this? So yeah, yes and no at the same time. This is on. No. You can always find f at 1, 2, right? If you really want to know the height of that critical point. Plug it in, it's going to be 1 plus 2 to the 4 minus 4 times 1 minus 32 times 4 plus 14. Who can tell me what it is? That would be nice.
shouldn't that also be part of the vertical point, like 1, 2,
That's a good question. That depends on the book in the United States, because they did not agree. Critical value should be inputs. Critical point should have input and output. So that's why I cannot give you the one single answer. It depends on the book we're using. So in this case, I can see where I think they mean that this is the point, but this point has the height. What is the height of this point? Anyone checked?
-37?
Thank you so much. -37, because I don't have this number here. So now we have the point in 3D, 1 to the x-axis, 2 units to the y-axis, and -37 deep. That is a critical point. And then we need to learn the second derivative test to check if the point, critical point we found, gives you minimum or maximum. So, question? Yes.
So for the whole function, is there only one critical point?
No, that's just an example with polynomial, like this. We're gonna have many. Just like in this picture, look at that. Just in this example. Yeah, I should not say no. Yes, in this example, actually, yes. But as you can see, there are mountains going on. Mountains and hills. And these, all of these, this will be critical point. This will be critical point. This looks like a critical point. This looks like a critical point. I think something behind over there may be critical point. And then sometimes it will be a fake critical point like over here, which neither maximum nor minimum. So that will be interesting. So all of these will come from solving those two equations. And then we'll have to check all the couples. If any of them, using second derivative test, gives us maximum or minimum. Yes.
How did you get the x equals 1 and y equals 2 again? Did you plug in 0 or?
Nah, I solved it. Yeah, I was wondering if someone gonna ask this. Thank you for asking. I solve it as 4. Let me do like so. 4x cubed equals to 4. Divide by 4. X cubed equals to 1. Take a cubic root. Cube root of 1 is 1. And the second one is 4y cubed is 32. Divide by 4. Y cubed is 8. Take a cubic root of 8. That is 2. Make sense? Yeah, I was wondering if someone gonna ask about the details. Did it help? So let me see. To check these points, you will have to use a second derivative test for every critical point we find. We will have to figure out the second derivative. Which second derivative? We have many. fxx or fxy or yx or yy, all of them.
Oh.
I know, and that's why multivariable calculus is complicated, because it's a lot of extra work. The more dimensions you have, second derivative test, the more dimensions you have, the more work you have to perform. So we will have to find all the second derivatives and build again a matrix or determinant D, putting them in order. Second derivative xx, second derivative yy. So the same ones go into the corners, and then x stays first in the first row, y, and then y goes first in the second row. This will be a crucial thing. This is called determinant. Put all the second derivatives in a table and then find this determinant. So this will be important part. You might be impressed that we do teach this business calculus class. They don't know that this is part of the calculus 3. They don't know that until I tell them, then they freak out. But we just tell them, let's learn how to find in business local maximum and local minimum, because business is multidimensional. Business has lots of variables, lots of dimensions, lots of variables included into the model. So they need to learn this, and we do learn this, second derivative test. So luckily this function is simple. So f of x is here in front of me. Let's find fxx, fxx, fxy, fyx, usually they are the same, fyy. Who can tell me? fxx,
12x squared.
12x squared, thank you. Because it was just 12x squared. It was just 4x cubed minus 4. fxy.
0.
How can you explain that this is 0?
There's no y.
There is no y in the first derivative with respect to x. Put these in the boxes because we will be, as you can see, we keep reusing them. So put them in the boxes. fxy is 0. Do you all agree on this? It's taking derivative with respect to the variable which is not there. So f of yx will be 0 as well, right? Because there's no x in the second line. So these are the same. And fyy is 12y squared. So the determinant of those two variables, x and y, imagine having more dimensions. So you'll have to have x, y, z, x, z, y, x, z, z, x, 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 y, 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 z, 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 and so on. This will look like xx is 12x squared, xy 0, yx 0, 12y squared, like so. So we're gonna stop on here and then do the quiz, because we're gonna continue with this topic on Friday. After this, it gets interesting but a little bit confusing. So I want to point more attention to this. Questions about this? What do you think?
Can we just leave it as that?
You will see on Friday, okay?